All right, this is section 10.3. We're going to start to give you a few applications associated with our vectors. If we didn't have the shortened school year, I'd be able to get to a lot more. I've condensed this down quite a bit, but just wanted to give you some insight into how these vectors can actually be applied to some physics applications, okay? So the two types of vectors we're going to focus on are velocity vectors and force vectors. So a velocity vector would be a vector that represents the speed and direction of an object. So the speed would be like the magnitude associated with the vector, and then the direction, of course, is based on where the object is headed, okay? And it would have an angle measure associated with it. In terms of force vectors, they represent the direction and the amount of force acting on an object, okay? Direction, of course, is where it's headed. Amount of force would be like the magnitude of your vector. Force vectors, if you can think like, let's say you're pushing a box across the floor. There is a force vector associated with it based on how much force you're pushing it with and where you're pushing it to, okay? All right, so this means we're going to have to represent our vectors in terms of their magnitude and their direction now. So let's say we have vector v with horizontal components of x and y. Now vector v I have drawn in red here, okay? And it's in standard position where its initial point is at the origin in the coordinate plane. Notice that vector v, it creates an angle theta between it and the positive x-axis, right? So that means that the horizontal component of that vector, x, it can be found by taking the magnitude of the vector itself and multiplying it by cosine of the angle theta that is between that vector and the positive x-axis. So your horizontal component is the magnitude of the vector multiplied by cosine of your angle theta, okay? And then the vertical component y would be nothing more than the magnitude of the vector multiplied by sine of your angle theta, okay? So this is really nothing new here. We're just applying our right triangle trigonometry to help us relate or represent these components in terms of magnitude and direction, okay? All right, so I have an example here. This would be an example of a velocity vector. We have a ball being kicked with a velocity of 20 miles per hour at an angle of 60 degrees, okay? Let's express the velocity as a vector in both component form and in terms of vectors I and vectors j, okay? So this velocity of 20 miles per hour, that's nothing more than the magnitude of the vector, and I'm going to call it vector v, okay? And then, of course, your angle of 60 degrees, that is like our direction theta, okay? So to find the horizontal component of this velocity vector, all we need to do is take our magnitude of 20 miles per hour and multiply it by cosine of 60 degrees. Now, 60 degrees is a nice angle here, right? Draw it out. Okay. So we can stay exact here. We can say this is equal to 20 times 1/2, right? Cosine of 60 is 1/2. So this gives us 10 for our horizontal component, okay? Vertically, we're going to find 20 times sine of 60 degrees, which is 20 times radical 3 over 2. And I'm going to simplify that to 10 radical 3. So that means this velocity vector in component form would look like 10 comma 10 radical 3. Or we could express it as 10 times the unit vector I plus 10 radical 3 times the unit vector j. Okay. Sometimes you'll have no choice. You'll have to round those components if the direction angle doesn't evaluate nicely, if it doesn't come from a special right triangle. Okay? All right, now it's your turn. You're going to go to practice 1 there. Pause the video, work through practice 1 yourself, and then you can come back to the video, check your work.